For this last example, let's find all of the same type of information, but from a different kind of function. So we don't have a polynomial here. Our original function f of x is 1 over x. So right off the bat, I'm going to be taking the derivative of this. In fact, I'm going to be taking the first and second derivative of this. So I might want to just rewrite my function up top here. F of x being 1 over x is really x to the negative 1. So just some algebra to start off with. My original function, 1 over x, I don't want to take the derivative like that. I'm going to rewrite it as x to the negative 1. And I'm going to find everything about this function. Critical numbers, inflection points, all that good stuff. So I'm going to start with the first derivative information and do my first step. So step 1, I'm going to take the first derivative of this and set it equal to 0. So I'm going to take my derivative, bring down my power, negative 1, x to the negative 2. And I need to set this equal to 0, which is pretty difficult for me to do when I have it written this way. So I'm going to take a second and rewrite this. I'm going to put that negative exponent down in the denominator where it belongs. So this is negative 1 over x squared equals 0. And a critical number either makes the first derivative 0 or undefined. So I'm looking at my numerator here, and I can't make that equal to 0. But I can make my denominator 0 so that I can make the first derivative undefined, right? If we make the denominator 0, we're making the derivative undefined. So I'm thinking, what would be squared to be 0? What number can I square and get 0? Well, x must be 0 in order for x squared to be 0 in the denominator. There's my critical number. It makes the first derivative undefined. So x equals 0 here. But let's go back for a second into the page where we defined a critical number, which is going to be way back in section 4.1. So looking back into your notes packet, we're going to work our way back to section 4.1, which is page 35. A critical number of a function is any number x in the domain of f. So what's important here is domain. So if I'm looking at this definition here, the x value has to be in the domain, which means we should be allowed to plug it in right away. It shouldn't make us take the square root of a negative number or divide by 0. And so I'm looking at this one, and it's kind of a strange example because I have a denominator here. So if we get back to the page we were on, page 50, this x value that's our critical number, is this even in the domain? Can I plug it into the original function right away? Well, if I plug that into the function, I would have 1 divided by 0. That cannot be plugged in. And it can't be factored to be plugged in. This is a vertical asymptote. So the value makes the derivative undefined, which is perfect. But since it's not in the domain, it's not a critical number. So there is actually none. There's no critical number because it's not in the domain. So this is just a weird example where we find something that makes the denominator 0 or undefined, and that's perfect. But then we go back to plug it into the original, and since we're not allowed to plug it into the original, it's not in the domain. Thus, it's not a critical number. So kind of a weird start, but I'm going to still use that number on my sign chart and see if I can find increasing, decreasing, relative max and min. So no critical number. First example we've seen of that, kind of rare, doesn't come up a lot in business calculus, but now we've seen it. Won't have to worry about it too much. I'm going to label this number. This makes f prime undefined, and it seems perfect, but it's not even in the domain, so we can't call it a critical number, but we can still use it on our sign chart. So I'm going to test a number before 0. So I'm going to test negative 1, and I'm going to plug it into my derivative. So I have negative 1 on the top, and I'm putting that over negative 1 squared. So the top is negative 1, so that's always negative. And the bottom, I'm doing negative 1 squared, which is going to be positive. So this whole interval here will be a negative divided by a positive, which is negative. So at first, I'm decreasing. After 0, I'm going to plug in maybe just a positive 1. My numerator of the derivative is still negative 1, so negative. And the denominator is going to be 1 squared, which is positive. So I'm, again, going to be negative here. So I don't have any sign change at my, what would have been a critical number. So since there's no sign change, and there's not even a critical number really, there's going to be no max or min on this. They can only happen at max or relative min can only happen at critical numbers, and I didn't happen to have one. So there's none for that. It's always decreasing, so there's actually no interval for increasing. And for decreasing, it is decreasing before and after 0. So negative infinity to 0, union 0 to infinity. So a lot of times I'll get the question, why not just write negative infinity to positive infinity? And the answer is that at 0, my derivative isn't actually negative. So to be decreasing, you have to have a negative derivative there. And when you plug in 0 to your derivative, you get an error out. This is undefined. So we can't really say whether it's decreasing or increasing because it doesn't have a positive or negative derivative. It's undefined. So it's safe to say that, yes, before 0, we have a negative first derivative, so we're definitely decreasing. And after 0, we have a negative first derivative, so we're also still decreasing. So there's my reason for that answer there. And now we're all done with the first derivative. And we can move on to inflection points and concavity, which means I'm going to repeat these same 2 steps all over again, but with the second derivative. So I'm going to kind of draw a line. And on the other side, I'm going to do the same 2 things. So I'm going to take the derivative and set it equal to 0 here. And I'm going to take the derivative of this version here instead of trying to do it when it's in the denominator. So I'm going to bring down my power. Negative 1 times negative 2 is going to be a positive 2 x to the negative 3 equals 0. And this is hard to solve for when I have that exponent written as a negative power. So I'm going to rewrite my second derivative as being 2 over x cubed, just putting that negative exponent in the denominator where it belongs. So a point of inflection is going to happen wherever we can make the second derivative 0 or undefined. So in this case, we're going to make the denominator 0 by making x equals 0. So I actually made f double prime undefined because I made the denominator 0, which is fine. That's still a possible point of inflection. Remember, that's only going to be a point of inflection if we also have concavity change. So I'm going to test and see before and after 0 if we have concavity changing or not. So this is special. This makes f double prime undefined. And let's see if this is really a point of inflection by seeing if concavity changes. So if I plug in anything to the left, maybe I'll plug in negative 1 into my second derivative now because I'm looking at concavity. So the numerator of my second derivative is always 2, so 2 is positive. And then I'm going to do negative 1 cubed. So negative 1 cubed is negative. So I am negative before 0, which means I'm concave down. So I'm going to look like part of an upside down U. And then after 0, I can plug in anything I want. Maybe I'll just plug in positive 1. This is my random test value. Plugging in the numerator is still 2. And the denominator is 1 cubed, which is 1. So I have a positive divided by a positive. Hey, we have a switch in concavity. We went from concave down, and we switched, and we're going to be concave up. So it looks like I would have a point of inflection here because I changed concavity. Well, for right now, before I find that y value of the point, I'm just going to write that I'm concave up from 0 to infinity. So I have a positive second derivative, and then from negative infinity to 0, I had a negative second derivative, so I was concave down. And now looking at my point of inflection is at 0, comma. This is when I plug back into the original function. And when I plug into the original function, I get 1 divided by 0. If you plug that in on your calculator, that is an error. Remember, 0 is not in the domain. It makes us divide by 0. So everything looks perfect. 0 made the second derivative undefined, which was good. And it had a change in concavity. But since it's not a point on the graph, this is not a point on the graph, it is not going to be a point of inflection. So there's actually none here. This is a hard function. We don't see these really hardly ever in business calculus, but I just wanted to show you one where, hey, the second derivative is 0, concavity changes, but since it's not a point on the graph, we can't plug it into the original function. We got an error. If it's not a point on the graph, then it's not going to be a point of inflection. So kind of a crazy example with no critical numbers, no point of inflection, no relative max or min. It was never increasing. Just kind of a strange looking function here, which gets us into curve sketching, our next section. What would this look like? We want to be able to see a picture, and that will kind of bring all these concepts together once we get an idea of what this graph looks like.